Now reflection. So here's a picture of geometrical optics reflection from a planar surface. So this is a planar, perfectly conducting surface. We'll keep it simple here. Although you can apply geometrical optics to non-perfectly conducting half spaces, we'll just keep it simple here and assume everything's perfectly conducting. And you know already that geometrical optics is related to this concept of stationary phase. So stationary phase point and point of reflection really mean the same thing. So here we have a source bouncing off a point of reflection given by the stationary phase point and then taking off as a reflection. Now in the geometrical optics context, we have these things that we now can refer to as an incident ray tube and a reflected ray tube. Ray tube, again, referring to that concept I've shown you on the last few slides. And then eventually, if we backtrack along the incident ray tube, there is some point, in 2 dimensions, just one. In 3 dimensions, there will be 2, but a caustic. And the caustic is the apparent source of all this. Now, is it the actual source? That depends on the details of the problem and how we apply geometrical optics. Now, how do we figure out what's going on with this reflected field? Remember, I said that the geometrical optics field is described completely by just 3 parameters, right? The direction, the polarization, and the wavefront curvature. Now, direction's pretty obvious here. Polarization, you can probably figure out pretty quickly. We'll address that in a moment. So let's just set that aside for now. Let's deal with wavefront curvature. We know from image theory that the curvature of the incident and reflected wavefronts is equal at the point of reflection. So in other words, whatever the curvature here is, curvature of the reflected geometrical optics field must be equal. And the way you can see that is from the simple construction where you backtrack along the ray tube and you can see an image source, right? So image theory says you can replace the perfectly conducting half space with an image source, and the image source is an equal distance below the ground plane, that the original source is above the ground plane, and from this you can immediately see that these 2 curvatures must be equal. What about other kinds of surfaces, curved surfaces in particular? Well, here's a convex surface. You can see here that reflection from a convex surface increases the curvature of the wavefront at the point of reflection. You can tell this right away from a simple application of Snell's law. Here's an incident ray. Angle of reflection equals angle of incidence, so it goes in that direction. Then we go over here, and following Snell's law, we see that the reflected ray goes in this direction. So we see that the rate at which these rays are diverging is increased by this reflection from the convex surface. If we consider a concave surface, we see just the opposite happens. Reflection from the 2 edges of a ray tube, we see that this seems to be making the rays converge. And in fact, you can imagine an intermediate case, which is the axisymmetric reflector case, in fact, where you have a feed illuminating a parabolic surface, and it makes the rays go exactly parallel to each other. Okay, so let us put this all on a mathematical foundation that we can use to write things like computer codes and to do the analysis that we need to do. So here's a scenario. I'll call the incident geometrical optics field E super I, the reflected geometrical optics field E super R, the distances SI and SR respectively. I'll also call these distances, by the way, or these directions of incidence and directions of reflection S hat I and S hat R. The point of reflection, I will give the name big Q. Big Q can be determined by Snell's law or by Fermat's principle. It's the stationary phase point. All 3 of those ideas are equivalent. The incident field, well, it's the geometrical optics form that I've already talked about. The reflected field is also a geometrical optics field, so it also has the form that I've already talked about. The only thing that's different is, well, what is the starting field. In other words, what is the field at the starting point, E super R at Q, where everything starts. There's a new spread factor because the wavefront curvatures have changed. So rho super I sub 1, for example, becomes rho super R sub 1. And the phase factor becomes e to the minus jk s super r as opposed to e to the minus jk s super I. Well, this part is pretty easy. Going from here to here is pretty straightforward because those two things are related by plane wave, planar surface reflection theory because we've already assumed that we've got this electrically large or asymptotically high frequency scenario going on, where we assume that everything is relevant emerges from the properties of the surface at the point of reflection. The wavefront curvatures are not difficult to find, but they require a little bit more thought, and we'll come back to that in a moment. What you can see is that the reflected wavefront curvatures will depend on the incident wavefront curvatures and also the surface curvature at point Q. We're going to have to come up with some math that describes how these transformations happen. So first, let's figure out how to get the reflected field at the point of reflection. The way we do this is using undergraduate plane wave theory. There's nothing special or exotic about this. What we do is we look at the incident and reflected rays and we define a plane of incidence. The plane of incidence is the plane in which the surface normal, n hat, and the direction of incidence lie. So you find the direction of incidence, this ray s hat super I, you find the surface normal, n hat, that's the plane of incidence. Now you can describe everything else in that plane. Now to work the problem, you simply identify this vector E hat perp, which points out of the page. And that's the same E hat perp over on the other side. And then you can define this vector E hat super I sub para, which is the cross product of this vector and this vector, right? You take the cross product of these two things, you get this. And similarly, if you take the cross product of these two things, you get this. So this defines what we refer to as a ray-fixed coordinate system, right? In fact, we have two ray-fixed coordinate systems here. Here's one, and here's the second one. One for incidence and one for reflection. This turns out to be a convenient way to decompose the problem because we can easily derive solutions in this case. We can separate the problem into these two components, which, by the way, are the same as transverse electric and transverse magnetic, and then work those problems separately and put them back together. So, for example, here I am taking the incident electric field and decomposing it into these two components, this being transverse magnetic, this being transverse electric. Those are the two components, and they're easy to find because I just take the incident field and take the dot product with the associated unit vectors. Very straightforward procedure. Now the reflected field is simply those same components. Right? With the new polarizations attached to them. Here they are. And then the appropriate reflection coefficients. So we know for TE, we have a reflection coefficient of -1. And for TM, we have a reflection coefficient of +1. So that's all there is to it. To get the reflected field at the point of reflection, we identify these two components, and then we construct this, applying the appropriate reflection coefficients and tacking on the appropriate polarization vectors. Very straightforward procedure. Now to get the wavefront curvature, here is the two-dimensional case. This is a diagram from your textbook. Unfortunately, the textbook uses slightly different notation than I use, so I've come up with a little table here where you can convert. In my notation, here is the bottom line. You can get the reflected wavefront curvature from the incident wavefront curvature, and the radius of curvature at the point of reflection, and the angle of incidence. So if I draw them up on this image from your book, here is the reflecting surface, here is the source, here is the incident ray. So rho super I is the wavefront curvature of the incident field at this point. The radius of curvature is this, and then theta super I is this distance. You know those three things, you can come up with the reflected wavefront curvature. Here's a nice little construction that justifies this equation. I'm not going to work through it, but it's not very difficult to do. It's simple geometry. But if you do this geometry, you'll see, in fact, that this is the relationship between those things. Another way you can make sure this is right is check it for some simple cases where you know what the result should be in advance. For example, what if the radius of curvature goes to infinity? What if the angle of incidence is 0, and so on, and make sure you get the right answer. But this is the bottom line. So we can apply all this to our example that we've used in previous lectures, that of the two-dimensional cylinder with a plane wave incident upon it. And we see this is the transverse electric case. We've previously shown the stationary phase solution gives a pretty good answer. Here is the angle phi, and we're measuring phi here, phi here. Here's the scattered electric field magnitude, and I'm showing both stationary phase and geometrical optics. Should not be surprising that those two techniques give the same answer. So this tells you one thing right away, is that stationary phase and geometrical optics are essentially the same thing. And they have the same limitations. They're valid only for specular directions, so they're valid in this range where you get a reflection-like mechanism, and they're totally bogus up here where the field is experiencing shadowing. This is the result for 10 wavelengths. This is the result for 1 wavelength, just to show you that kind of the right things happen as the dimensions of the cylinder change. So, as expected, GEO is essentially the same as the physical optics method evaluated using stationary phase. Shares the same features as the physical optics stationary phase solution. Very fast, that is, there's no integration. It's good where specular scattering is expected, that is reflection. But it gives you a bogus prediction in the shadowing region. That is, it doesn't tell you what is happening in the shadowing region. And like the PO stationary phase method, it's physically intuitive, perhaps even more so. That word geometrical and the term geo is for real. Everything becomes geometrical. It kind of works the way you intuitively think it might. And where the math comes in is in calculating the polarizations and the wavefront curvatures. The 3D case, computing the wavefront curvatures. This is the remaining problem now. For a full discussion of this problem, my personal recommendation is this particular paper, Quimjian and Pathak, 1974 paper that appears in Proceedings of the IEEE, which explains exactly how to do this in excruciating detail. The solution for this general case that's described in this paper is pretty complex, but it's completely tractable. It's not that it's impossible to do, or that's too complicated to understand, or that it's computationally difficult. Neither of those two things is true. It just involves a lot of pieces that you have to understand. Fortunately, we do not often require the general solution. Far more common is that we need the solution for spherical wavefront incidence. Because remember, most things like feed antennas in the far field produce radiation which can be viewed as being spherical. In other words, the far field of feed antennas can be interpreted as a spherical wave. So this simpler problem of spherical wavefront incidence is often all we need. So here is the relevant equations for that special case of the spherical wavefront incidence. In that case, and this is incidence just to be perfectly clear, because you may not have a spherical wavefront after reflection. So here are the reflected wavefront curvatures in the principal planes. And remember, the principal planes are those planes in which the curvatures are maximum and minimum. And you can get these by identifying the angle of incidence, the radii of curvature in the principal planes. Then you also have to know how the principal planes are oriented with respect to the surface normal. And that's not too hard. That's just a picture that you can draw. And then you apply this equation and you get the curvatures. So it looks intimidating. It's a rather complex equation, but it's relatively straightforward to compute, and it's pretty straightforward to check. Because once you code this up, for example, in a computer program, you can check special cases, like what happens when one or the other surface curvature is 0. That is, its radius of curvature is infinite. What happens when you have angles of incidence which are 0, and check and make sure it works for all those special cases. So whenever you do a problem and you work this equation, I highly recommend you do that. You make those checks to make sure that this equation is working the way it's supposed to. Okay, concluding remarks. Geo is usually the fastest, simplest way to compute scattering from electrically large and electrically smooth surfaces when reflection dominates. Geo finds numerous applications in the analysis and design of large reflector antennas. Just to name 2 ways that we use Geo in this kind of work, here they are. One is a technique known as Geometrical Optics Aperture Integration, or GeoAI, which is used to analyze the main beam and largest side lobes of a reflector. What we do in GeoAI is we imagine a reflector being fed by a feed, and the feed and the signals from the feed bounce off the main reflector, and then we define an aperture in front of the reflector, and we determine the electric field in that aperture. Then we can use aperture theory to determine the main beam characteristics and the characteristics of the first few side lobes using everything we've already described in previous lectures. So this technique, GeoAI, is a combination of those 2 methods. Geometrical optics to figure out what the aperture field is, and then aperture integration to figure out what the pattern is. The other way we use geometrical optics is as part of a technique known as GTD, or the geometrical theory of diffraction, or what we'll call UTD, which is a uniform geometrical theory of diffraction. In these methods, GTD and UTD, geometrical optics is the way that you compute ray contributions associated with line of sight and reflection. So in GTD and UTD, you compute total fields, including diffraction, by summing diffraction terms with contributions from reflection and line of sight. And the latter 2 are obtained by geometrical optics. This concludes this lecture on geometrical optics.